Jupiter's magnetic field does not end at its boundary. No, it extends far beyond that. In fact, it trails behind the planet for millions of kilometers in an enormous cosmic tail. We call it the magnetotail, but what is it exactly? And what is it doing all the way out there? You know, scientists have been observing the magnetotail for decades. They've sent probes into it. They've seen strange light emissions from it. But even today, we still don't fully understand this feature, not by a long shot. So in this video, we're going to do our best to decode one of the solar system's greatest mysteries. But first, if you love space exploration and science, then subscribe to our channel and hit the bell icon to be notified about new videos. Alright, let's get started. Our story begins, like so many of ours do, with Galileo Galilei. Way back in 1610, he observed Jupiter's four largest moons, which are now named after his patron, the Medici family. And as he watched those moons orbiting the planet, he noticed something odd. The moons Io and Europa were unusually bright, brighter than they should have been. Galileo couldn't figure out why, but these days we know the reason. It's because these two moons, plus another one named Ganymede, are covered in electrically charged particles of plasma that are pulled off their surfaces by Jupiter's immense magnetic field. You see, Jupiter is by far the most magnetically powerful planet in the solar system. Its magnetic field is more than twice as strong as Earth's and extends more than 90,000 kilometers from the planet. That's more than half the distance between Earth and the Moon, but unlike Earth, which has a mostly symmetrical magnetic field, Jupiter's magnetic field isn't perfectly round. In fact, it's lopsided and stretched out along Jupiter's axis of rotation. This is due to the planet's rapid rotation, which whips the plasma of its atmosphere up into a colossal vortex known as the Great Red Spot. The planet's magnetic field gets caught up in the storm and gets dragged into long, thin magnetic field lines that trail away from the planet. Now, the magnetotail is the part of the magnetic field that extends more than 2 million kilometers from the planet. And the strange thing about it is that it is filled with plasma that is moving in the opposite direction as Jupiter rotates. So, as the planet spins around once every 10 hours, the plasma in its magnetotail is moving towards the east. This plasma comes from several different sources. There's the volcanic moon Io, which spews plasma into the magnetotail via its volcanic activity. Then there's the planet itself, which constantly bombards its magnetotail with high-energy particles. And lastly, there's the solar wind, the steady stream of charged particles that flows outwards from the sun. When the solar wind hits Jupiter's magnetotail, it gets funneled down into the planet's atmosphere via its magnetic field lines. And believe me when I say that this is a wild ride for those particles. They're accelerated to speeds of up to 400 kilometers per second, nearly 10 times the escape velocity from Earth. This means that they can literally orbit Jupiter multiple times before finally crashing into the planet. Now, scientists aren't entirely sure what happens to the particles after that, but they think that they eventually make it into the planet's interior, where they heat up its metallic hydrogen ocean. But while those particles are whipping through the magnetotail, they're emitting ultraviolet radiation that's so bright, it's detectable from Earth. In fact, one of the first hints of Jupiter's magnetotail came in 1979 when NASA's Voyager 1 probe detected an unexpected surge in ultraviolet emissions coming from the planet. Of course, the probe was far from the first to spot the magnetotail. Back in 1951, the American astronomer John H. Nelson had already identified a faint, fuzzy extension of Jupiter's magnetic field using radio waves. But Voyager 1's discovery of the ultraviolet emissions helped confirm that Jupiter had a proper magnetotail. Unfortunately, Voyager 1 didn't have enough fuel to venture too far into the magnetotail. So that remained one of the great mysteries of our solar system. What is this thing doing all the way out there? Well, we got our first clue in 1983 when NASA's second Galileo spacecraft began sending back data from its flyby of Jupiter. It turned out that the magnetotail wasn't just some fuzzy blob. No, it had structure. It looked a lot like a comet with a head and a tail. The head, also called the magnetosheath, was a relatively dense, lumpy region of plasma near the planet. Meanwhile, the tail itself was strangely empty of plasma, but it was surrounded by a thin shock wave that indicated something massive was going on out there. To understand what was going on, let's look at what's happening at Jupiter's surface. As we said earlier, the planet's magnetic field lines extend down into its atmosphere and funnel charged particles from the magnetotail into its interior. These particles excite the atmospheric gases, causing them to emit light. In other words, Jupiter's magnetotail helps power the auroras on the planet's surface. And it turns out that the auroras on Jupiter are some of the most energetic phenomena we've ever seen in our solar system. They can be 1,000 times more luminous than Earth's auroras, giving them an ethereal glow that can be seen from Earth without a telescope. But while Galileo observed these auroras during its flyby, it couldn't actually capture images of them. The spacecraft was simply too far away. We didn't get good views of Jupiter's auroras until over a decade later when NASA's Hubble Space Telescope came online. Using Hubble, astronomers could finally observe Jupiter's dynamic auroras in all their glory. But they soon realized that something was weird about them. The auroras weren't centered on Jupiter's magnetic poles. Instead, they were shifted off to the sides by about 55 degrees. Now, at first, astronomers thought that this was a flaw with Hubble. Surely Jupiter's auroras would be symmetrical, right? But no, further observations confirmed that the auroras were indeed offset. Something was pulling them to the side and creating a massive conundrum for scientists. How could Jupiter's magnetic field be so lopsided? After all, the planet is perfectly round. Well, the answer lies in Jupiter's rapid rotation. As the planet spins, it drags its magnetic field with it. But the field lines can't spin with the planet forever. Eventually, centrifugal force wins out and the field lines break and reconnect, shifting the magnetic poles away from the rotational poles. And if you want to visualize what this looks like, just take a bunch of long, thin ropes and start spinning them around. At first, the ropes will form a tight, symmetrical bundle, but eventually the centrifugal force will tear the ropes apart and spread them into a flat pancake. This is essentially what's happening to Jupiter's magnetic field lines. But wait, doesn't that mean that Jupiter's magnetic field is constantly changing? Like, if it breaks and reconnects, then wouldn't the magnetotail disappear every few years? Well, yes, but it reforms quickly. And that's because Jupiter's magnetic field isn't just being dragged out into space, it's actually being pulled by another planet, Saturn. That's right, over 100 years ago, scientists realized that Jupiter and Saturn's magnetic fields were interacting with each other. In fact, they were so close to each other that their magnetic fields were overlapping. And this overlap created a tangled mess of magnetic field lines that extended as far out as Pluto. So when Jupiter's magnetic field gets torn apart by centrifugal force, Saturn's magnetic field acts like a safety net, catching the field lines and preventing them from drifting too far away. This means that although the shape of Jupiter's magnetotail changes all the time, it always stays tethered to the planet. But wait, if Saturn is helping keep the magnetotail tethered to Jupiter, how is it possible for the tail to be 2 million kilometers long? Well, that's because Saturn's magnetic field isn't as strong as Jupiter's. It can only pull the field lines so far before the centrifugal force tears them apart again. In other words, Jupiter's magnetotail is a never-ending tug of war between the planet's rotation and the gravitational pull of Saturn. But there's a whole lot more going on here. For example, the magnetotail is constantly bombarded by the solar wind, which creates ripples and bubbles in the plasma. Plus, the moons of Jupiter are always getting in the way. Take the moon Amalthea, for instance. It orbits Jupiter only 200 kilometers from the planet's surface, and according to NASA, it gets bombarded by hundreds of tons of plasma rain every second. This plasma is blown out of Jupiter's magnetotail and onto the moon's surface, which creates a thin atmosphere of sorts. But while this is bad news for poor little Amalthea, it could be good news for us. You see, Jupiter's magnetotail is such a massive structure that it often extends well beyond Earth's orbit. And when it does, it can interact with our planet's magnetic field. In fact, it is believed that Jupiter's magnetotail is responsible for triggering some of Earth's most intense geomagnetic storms. Now, these storms can wreak havoc on our planet's magnetic field and disrupt important things like our telecommunications and our GPS systems. So while we might not be able to protect ourselves from the wrath of Jupiter, we can at least learn how to predict it. Thanks to NASA's stereo spacecrafts, we can now track Jupiter's magnetotail as it moves through space. And while we still have a lot to learn about this enigmatic structure, we can be thankful that it's not aimed at us. If you enjoyed this video, check out our previous video about Jupiter's moon Europa, which is full of even more exciting discoveries. Thanks for watching, and we'll see you next time.